sound of deep, resonant hums, mixed with ethereal stellar wind effects in the vast, unending future, long after the final star has flickered and died. When galaxies have dissolved into a whisper of cosmic dust, only one type of object will endure. They will not illuminate the darkness. They will not wander the cosmos. They will not cradle life. Yet they will reign supreme over all that remains. These are the black holes, the ultimate engines of gravity, the most extreme manifestations of mass, and perhaps the final, inevitable stage of the universe's evolution. Imagine a power so immense that it dictates the fate of everything. Every atom that once formed a planet, every star that once warmed a solar system, every galaxy that spun in a celestial dance, even light itself, is ultimately subject to their inescapable pull. In the presence of a black hole, the very laws of physics as we know them are warped and rewritten. Time, the constant river we all flow upon, slows to a near standstill. Space, the fabric of reality, bends and contorts in unimaginable ways. The line between existence and absolute nothingness becomes profoundly, terrifyingly blurred. But how did these cosmic tyrants come to be? To truly grasp why the universe will one day belong entirely to black holes, we must journey back to their violent and spectacular origins. We need to witness the cataclysmic deaths of the very first massive stars, explosions that seeded the cosmos with the building blocks of life, but also gave birth to the first seeds of eternal darkness. This is the story of the universe's final chapter, an era where darkness doesn't just fall, it rules. What exactly is a black hole? It's not a hole in the traditional sense, but rather an incredible amount of matter packed into an impossibly small space. Think of a star 10 times more massive than our sun, squeezed into a sphere about the size of New York City. The result is a gravitational field so strong that nothing, not even light, can escape its grasp. This boundary, the point of no return, is called the event horizon. Crossing it is a one-way trip into the unknown. There are several types of black holes. The most common are stellar mass black holes, born from the collapsed cores of giant stars. When a star at least 3 times the mass of our sun runs out of fuel, it can no longer support its own weight. The core implodes under its own gravity, triggering a supernova explosion that blasts the star's outer layers into space. What's left behind is a singularity, a point of infinite density, cloaked by its event horizon. For billions of years, these stellar remnants have been quietly accumulating across the cosmos. Then, there are the supermassive black holes. These are the true monsters, with masses millions or even billions of times that of our sun. We find one at the heart of nearly every large galaxy, including our own Milky Way. Sagittarius A*, our galactic center, is a supermassive black hole about 4 million times the mass of the sun. How did they get so big? Scientists believe they started small and grew over eons, voraciously feeding on surrounding stars, gas, and dust, and even merging with other black holes in colossal cosmic collisions. Now, let's fast forward to the distant future, the era known as the black hole era. After trillions upon trillions of years, star formation will have long ceased. The universe will be a cold, dark, and expanding void. The remaining planets, stars, and galaxies will have been slowly, methodically consumed by black holes or flung into intergalactic space. All that will be left are these gravitational behemoths, drifting silently through the eternal night. They will be the only organized structures in a universe that is otherwise decayed into scattered low-energy particles. But even black holes are not eternal. Thanks to a phenomenon predicted by Stephen Hawking, known as Hawking radiation, black holes slowly evaporate over incomprehensibly long timescales. They lose mass by emitting tiny particles from their event horizon, a process that is incredibly slow for large black holes, but a definitive end nonetheless. A solar mass black hole would take around 10 to the power of 67 years to evaporate. For the largest supermassive black holes, it could take 10 to the power of 100 years, a number so large it's functionally meaningless to the human mind. When the last black hole finally radiates away into nothingness, it will signal the true end of the universe as we know it, leaving behind only a faint cold soup of fundamental particles. It's a sobering, yet awe-inspiring thought, that the most powerful objects in the cosmos will also be its final inhabitants, presiding over an empire of absolute darkness before fading away themselves. The story of black holes is the story of the universe's ultimate fate. They are the beginning of the end and the end of everything. Have you ever looked up at the night sky and wondered about the darkness between the stars? What if I told you that some of that darkness isn't empty space, but a place where gravity is so strong that even light can't escape? Today, we re-journeying into the heart of one of the universe's most extreme and fascinating phenomena, the black hole. Black holes aren't just cosmic vacuum cleaners. They are born from the dramatic death of giant stars. Imagine a star, a massive one, far bigger than our sun. For millions of years, it's in a delicate balance. Deep in its core, nuclear fusion creates a tremendous outward blast of energy, perfectly fighting against the relentless inward crush of its own gravity. It's a cosmic arm wrestle that lasts for eons. But this battle can't go on forever. Eventually, the star runs out of fuel. The fusion engine sputters and dies. But suddenly, there's nothing left to push outwards. Gravity, the patient, silent force, finally wins. In a fraction of a second, the star's core collapses under its own colossal weight. What happens next is straight out of science fiction. If the star is massive enough, at least 3 times the mass of our sun, nothing in the known universe can stop this collapse. The very atoms that make up the star are crushed. Protons and electrons are forced together to become neutrons. Even the incredible pressure of these neutrons isn't enough. The core continues to fall inward, compressing into an infinitely dense, infinitely small point. We call this a singularity. At this point, our understanding of physics breaks down. The core has collapsed so violently that it has punched a hole in the fabric of space-time itself. Imagine placing a bowling ball on a trampoline. It creates a dip. Now imagine a bowling ball with infinite weight. It would create a bottomless pit. That's what a black hole does to space-time. And surrounding this singularity is the event horizon. This isn't a solid surface you could touch. It's an invisible boundary, the point of no return. Once you cross the event horizon, there is no escape. The pull of gravity is so immense that all paths, every single direction, lead inward toward the singularity. Even if you were in a spaceship traveling at the speed of light, you couldn't get out. It's the ultimate one-way trip. The idea of these dark stars isn't entirely new. Back in the 18th century, thinkers like John Michell and Pierre Simon, Laplace wondered if an object could be so massive and dense that its escape velocity would be greater than the speed of light. They were on the right track, but they were missing a key piece of the puzzle. That piece arrived in 1915 with Albert Einstein and his revolutionary theory of general relativity. Einstein completely changed our view of gravity. He showed us that gravity isn't a mysterious force pulling things together. It's the curvature of spacetime caused by mass and energy. The more massive an object, the more it warps the spacetime around it. Just a year later, a German physicist named Karl Schwarzschild was studying Einstein's equations and found a startling solution. He described a point of infinite density that would bend spacetime so steeply it would create an event horizon, a region from which nothing could escape. He had mathematically described a black hole. Interestingly, Einstein himself didn't believe these objects could actually exist in the real universe. He thought they were just a weird quirk in the math, a mathematical absurdity. But as we've explored the cosmos, we've found that the universe is often stranger and more wonderful than we can imagine. The universe, it turns out, is full of black holes. The very first ones were born in the cosmic dawn, shortly after the Big Bang. In that early era, the universe was filled with colossal stars, hundreds of times more massive than our sun. These population 3 stars were made exclusively of hydrogen and helium, and they burned incredibly hot and fast. Their lives were short and violent. When they ran out of fuel, they didn't just fade away. They collapsed directly into black holes, leaving behind the first gravitational seeds. These primordial black holes were the ancestors of the giants we see today. Over billions of years, these seeds grew. They feasted on surrounding gas and dust. They collided and merged with other stars and other black holes, growing larger and larger with each meal. They sank to the centers of young galaxies, acting as gravitational anchors, pulling matter together and helping to shape the very structure of the cosmos. and this process led to the creation of the supermassive black holes. These are the undisputed titans of the universe, with masses millions or even billions of times that of our Sun. Today, we believe that nearly every large galaxy, including our own Milky Way, has one of these behemoths lurking at its core. Right now, our entire solar system is in a grand cosmic dance, orbiting the center of the Milky Way. And what are we dancing around? An invisible anchor? A supermassive black hole named Sagittarius A**. It's about 4 million times the mass of our Sun, and it sits silently at the heart of our galaxy. Its immense gravity orchestrating the orbits of billions of stars. Without it, the Milky Way as we know it might never have formed. This is the great paradox of black holes. They are born from an act of ultimate destruction, the death of a star. Yet they are engines of creation, helping to build and structure entire galaxies. They are the epitome of darkness, swallowing light itself. Yet by studying them, we illuminate the deepest secrets of gravity and the universe. They are both destroyer and architect, a fundamental force of cosmic chaos and order. But the story doesn't end there. Not all black holes are silent, invisible anchors. Some are the roaring, brilliant hearts of the most energetic objects in the cosmos. When a black hole actively feeds, a spectacular transformation occurs. The matter swirling into it forms a blazing, superheated disk, brighter than 1 trillion stars. These are the quasars, the lighthouses of the distant universe, powered by the very darkness they inhabit. They show us the incredible power that can be unleashed from the edge of oblivion. If stellar black holes are the ashes of dying stars, then supermassive black holes are the cosmic monarchs, the true rulers of galaxies. They lurk at the heart of nearly every large galaxy we've ever observed. Some weigh as much as millions of suns, others, billions. The largest one we know of, Ton 618, packs the mass of more than 66 billion suns. Its gravitational empire is so vast that its event horizon could swallow our entire solar system. It's not once, but several times over. It's mind-boggling. But how do such giants even come to exist? How can a universe that started with subatomic simplicity give birth to something so colossal, so extreme, and so utterly dominant? We think there are a few possible pathways that forge these cosmic titans. One idea starts with the very first generation of stars, known as population 3 stars. These early giants were enormous, and when they died, they left behind black holes with masses around 100 times that of our Sun, over cosmic eons. Through a process called accretion, a steady diet of gas, dust, and unfortunate stars, and through violent mergers during galactic collisions, they could have swelled into the monsters we see today. Another theory suggests a faster route, direct collapse black holes. In the dense, pristine gas clouds of the early universe, entire clouds might have collapsed directly into black holes, skipping the whole stellar phase entirely and starting life as objects thousands or even millions of times the mass of the Sun. Whichever path nature chose, the result was the same. Just a few 100 million years after the Big Bang, the universe was already home to some of these leviathans, and they announced their presence with an incredible, universe-spanning brilliance. When matter falls toward a black hole, it doesn't just vanish quietly. It forms a hot, spinning disk-can accretion, disk-where friction and magnetic fields heat the infalling gas to millions of degrees. As this material spirals inward toward its doom, it releases enormous amounts of energy, sometimes outshining entire galaxies. We call these radiant monsters quasars, just short for quasar-stellar radio sources. When astronomers first spotted quasars in the 1960s, they just looked like faint, star-like points of light. But when they analyzed their spectral signatures, they discovered something astonishing. These objects were billions of light-years away, yet they were brighter than any known galaxy. The only engine powerful enough to explain such luminosity was matter falling into a supermassive black hole, converting gravitational energy into light with staggering efficiency. At their peak between 10 and 12 billion years ago, quasars ruled the cosmos. This period is known as the quasar epoch, and during this time, the universe was ablaze with them. Each one was the blazing heart of a young, growing galaxy, fed by massive torrents of gas and dust left over from the formation of cosmic structures. But quasars didn't just light up the universe. They actively shaped it. The powerful winds and jets they blasted out could blow material clear out of galaxies. This process, called feedback, regulated star formation and influenced how cosmic structures grew. It might be one of the key reasons why galaxies like our own Milky Way have the size, shape, and star formation rates we observe today. They are cosmic architects, sculpting the universe on a grand scale. When galaxies collided, their central black holes would eventually merge as well. These titanic unions sent gravitational waves the universe's most. Silent yet powerful music crippling through the very fabric of space-time. Each merger forged an even larger black hole at the center of the newly formed galaxy. Over billions of years, through countless mergers and cosmic feasts, the universe's black holes continued to grow, even as the cosmos itself expanded and cooled. Today, the era of blazing quasars is long past. The universe is a much quieter, calmer place. Most supermassive black holes are now dormant sleeping giants that only feed occasionally, when a stray gas cloud or star ventures too close. But even in their slumber, their influence endures. Their immense gravity stabilizes the centers of galaxies. Their ancient jets seeded intergalactic space with heavy elements, and their very presence anchors the cosmic dance of billions of stars. Our own Milky Way's central black hole, Sagittarius A*, is relatively small and quiet, but when a rare object, like a gas cloud, gets too close, it awakens briefly, emitting bursts of radiation that echo across our galaxy, a reminder of the power lurking at our galactic core. And then, in 2019, humanity finally glimpsed the unseeable. For the first time in history, we imaged a black hole, the glowing ring of light around the supermassive black hole in galaxy M87, 55 million light-years away. This wasn't an artist's impression. This was real, assembled from the data of telescopes spread across our entire planet, synchronized to function as one Earth-sized eye. The Event Horizon Telescope revealed a silhouette of shadow cast by gravity itself. The image confirmed Albert Einstein's predictions with astonishing precision decades after his death. Supermassive black holes define structure, drive galactic evolution, and hold galaxies together. But even as we celebrate these incredible discoveries, we face a deeper mystery, one that seems to defy both logic and physics. What happens to the information that falls inside a black hole? Is it lost forever, violating the fundamental laws of physics? Or does the universe somehow, in a way we can't yet comprehend, keep its books balanced? That is perhaps the greatest question these giants pose. For centuries, we've pictured black holes as the universe's ultimate dead ends. Cosmic graveyards where stars, planets, and even light itself vanish without a trace. A one-way ticket to oblivion. But what if that's not the whole story? What if these cosmic monsters are actually hiding one of the deepest secrets of reality? In the 1970s, the brilliant mind of Stephen Hawking turned our understanding of black holes completely upside down. He discovered that they aren't entirely black after all. Due to bizarre quantum effects right at the edge of no return, the event horizon black holes slowly leak energy. Sphinx low, now known as Hawking radiation, means that over immense, almost unimaginable timescales, black holes can actually evaporate. Trillions upon trillions of years from now, even the most gigantic black holes might simply disappear. But this raises a mind-bending question. If a black hole can vanish, what happens to everything it swallowed? Think about it. Every star, every planet, every single particle contains information. Its spin, its location. Fundamental rule of physics, both classical and quantum, is that information can never be destroyed. It can be scrambled, rearranged, or hidden, but it can never be truly erased from existence. Yet, Hawking's original calculations suggested something impossible. The information swallowed by a black hole was lost forever when it evaporated. This massive contradiction is known as the black hole information paradox. It's one of the most profound and frustrating puzzles in all of modern science. It pits our two best theories of the universe, Einstein's general relativity and quantum mechanics, against each other in a battle for the soul of physics. So, where does the information go? Scientists have been wrestling with this for decades, and the proposed solutions are even stranger than the problem itself. One possibility is as terrifying as it is simple. The information is just lost. Gone. This would mean that in the extreme gravity of a black hole, the fundamental laws of quantum mechanics break down. If this is true, we'd have to rewrite our entire understanding of the universe from the ground up. It would be like discovering that the law of conservation of energy just stops working sometimes. It's a radical idea that most physicists are reluctant to accept. Another, more popular theory is that the information isn't lost at all, it escapes. The idea is that the information is subtly encoded in the faint Hawking radiation that leaks out. It wouldn't be easy to read. It would be like trying to reconstruct a burned book from its smoke and ash. But in principle, the story of everything that fell into the black hole is still there, just incredibly scrambled. This idea leads to even wilder concepts, like the holographic principle. The holographic principle suggests that all the information contained in a volume of space like our three-dimensional universe can be described by a theory living on the boundary of that space, like a two-dimensional surface. It's like saying our reality is a hologram projected from a distant, flat screen. In this view, the information that falls into a black hole never truly crosses the event horizon. Instead, it gets smeared across the surface and is slowly radiated back out into the universe. Then there's an even more bizarre idea called black hole complementarity. This theory suggests that reality depends on your point of view. For someone falling into a black hole, their information passes through the event horizon with them, seemingly lost forever. But for someone watching safely from a distance, that same information is seen to be smeared across the horizon and radiated away. So, is the information inside or outside? The mind-bending answer is both. The two realities never contradict each other because the person falling in can never send a message back out. It's a strange but elegant way to make relativity and quantum mechanics play nice. These aren't just abstract thought experiments. They're at the very heart of the quest for a theory of everything, a unified theory of quantum gravity that can describe both the immense scale of the cosmos and the tiny realm of subatomic particles. Black holes are the natural laboratories where gravity is so strong that quantum effects can't be ignored. Cracking the information paradox could be the key that unlocks the next great revolution in physics. And the paradox is just the beginning of the mysteries. What lies at the very center of a black hole? Our current equations predict a singularity, a point of infinite density, where the laws of physics, as we know them, completely break down. Is it truly a point of infinity? Or does some new, undiscovered physics take over? Could these singularities be gateways to other places, or even other universes? The concept of wormholes, or Einstein-Rosen bridges, suggests that black holes might connect distant regions of space-time, acting as cosmic shortcuts. While it remains purely theoretical, it's a tantalizing possibility that continues to fuel science fiction and scientific inquiry alike. There's also the question of primordial black holes. Scientists theorize that tiny black holes might have formed in the chaotic moments just after the Big Bang. If they exist, they could be scattered throughout the universe. Could these ancient relics be the mysterious dark matter that holds our galaxies together? Are they just long-extinct remnants of a violent cosmic birth? In this way, black holes are not just objects, they're questions. They are cosmic enigmas that challenge every assumption we have about space, time, matter, and information itself. They push the absolute limits of our knowledge and force us to confront the deepest mysteries of existence. And their significance extends far beyond scientific curiosity. Black holes are central to the ultimate fate of the universe, the far distant future, long after the last star has burned out, and galaxies have drifted apart into a cold, dark emptiness. Black holes will be the last major structures remaining. They will be the silent, enduring sentinels of cosmic history, the final keepers of the story of everything that ever was. In their slow evaporation, they will hold on to the final echoes of our universe. A testament to every star that shone, every planet that formed, and every bit of information that made reality what it is. Start with visuals of a starry night sky, then telescopes, and animated radio signals traversing the globe black holes. They're distant, extreme, and exist in realms so far beyond our everyday lives it's hard to even imagine. Yet, their influence touches us in surprisingly profound ways, shaping our understanding of the universe, driving incredible technological leaps, and expanding the very boundaries of human imagination. Visuals shift to an animation of Sagittarius A*, the supermassive black hole at the center of the Milky Way. From here on Earth, we can't see black holes directly. Their defining feature, The event horizon swallows all light. So how do we know they're there? We follow the clues left by gravity's invisible hand. We see stars orbiting unseen masses, gas clouds spiraling at mind-boggling speeds, and powerful bursts of radiation from accretion disks that pinpoint the universe's most extreme objects. This is exactly how we discovered Sagittarius A*, right in our own galactic backyard. For decades, astronomers tracked the frantic dance of stars, measuring the gravitational pull of an object for a million times the mass of our sun. Nothing else could explain it. Show footage of massive telescopes like Keck, the VLT, and the array of dishes that make up the Event Horizon Telescope. The quest to understand black holes has led to some of the most ambitious projects in human history. Take the Event Horizon Telescope. It synchronized radio observatories across the entire globe to create a virtual telescope the size of Earth itself. Its groundbreaking first image in 2019 showed us the shadow of M87*, a supermassive black hole 55 million light-years away. This wasn't just a picture, it was proof. We had a direct view of an event horizon, the point of no return. These observations have deep implications for physics, testing Einstein's general relativity in the most extreme gravitational fields imaginable. By doing so, we refine our understanding of the fundamental forces that govern everything and validate the models that describe the evolution of our cosmos. Animation of gravitational waves rippling through a grid representing space-time is detected by LIGO, but we don't just see black holes anymore. We can also here, them. Black holes reveal themselves through gravitational waves ripples in space-time caused by cataclysmic events like two black holes merging. In 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected these waves for the first time, sensing the collision of two black holes over 1 billion light-years away. This was a monumental achievement. The first time in history, humans could listen to the universe's most violent events. We are no longer limited to light. We are now listening to the rhythm of gravity itself. Show scientists at control panels, data streams, and then transition to practical applications like medical MRI scans and GPS animations. Beyond the cosmic revelations, studying black holes drives practical technological advances right here on Earth. The high-precision detectors, ultra-cold cryogenic systems, and complex algorithms developed for astrophysics have found their way into medical imaging, satellite navigation, and big data analysis. Even the theoretical work, like simulating the chaos of accretion disks and relativistic jets, pushes the limits of supercomputing, paving the way for future innovations in countless other fields. The technology we build to look out at the universe often ends up helping us look deeper into our own world. Montage of science classrooms, kids looking through telescopes, and public science exhibits. And then there's the sheer power of inspiration. Black holes challenge our fundamental concepts of space, time, and reality. They force us to confront our place in the universe as a small, fragile species, yet one capable of understanding phenomena billions of light-years away and billions of years old. They are the ultimate cosmic puzzle, inviting us to ask bigger and bolder questions about who we are and where we came from. Visuals zoom out from Earth to a grand cosmic scale. Showing the Milky Way galaxy culturally, black holes have become powerful symbols of mystery, the unknown and the limits of our knowledge. In films, books, and art, they represent the uninspiring scale of the universe. They're a constant, humbling reminder that the cosmos is far stranger and more magnificent than woman the Ruchanzingen Sonung Sound. The view settles on a silent, vast galactic web, soft light tracing the gravitational connections ultimately. Black holes demonstrate a profound truth. Even the most distant alien phenomena are connected to us. Through observation, experimentation, and imagination, we can explore what once seemed completely unapproachable, the very fabric of reality. And yet, for all we've learned, a horizon remains that we can never cross. The deeper we probe, the more profound the questions become. Pause, with music swelling to a tone of awe and suspense. In our next segment, we'll explore the incredible scientific journey of discovery from the first theoretical predictions that were once dismissed as mere mathematical quirks to the modern era of giant telescopes, complex simulations, and direct observations. We all trace the footsteps of the brilliant minds who transformed black holes from abstract curiosities into the observable, universe-shaping pillars of the cosmos we know today. Have you ever wondered about those cosmic voids in space, the ones that swallow everything, even light? They're called black holes, and for the longest time, they were just ghosts hiding in complex math problems. Imagine this. 100 years ago, even the great Albert Einstein thought the idea of a black hole was too wild, too extreme to be real. They were just scribbles on a blackboard, a mathematical curiosity. But how did we go from doubting their existence to actually taking a picture of one? Our story starts back in 1916, while the world was in turmoil. A physicist named Carl Schwarzschild was busy solving Einstein's brand new equations for general relativity. What he found was shocking. A solution that described a point of infinite density, a dark star surrounded by a boundary of no return, what we now call an event horizon. Einstein himself waved it off as a theoretical quirk, something that couldn't possibly exist in the real universe. But that quirk laid the groundwork for everything we know about black holes today. For decades, Schwarzschild's idea remained on the shelf, a puzzle for theorists. But then, the 1960s arrived, and everything changed. Astronomers started pointing their new radio telescopes at the sky and found something bizarre, incredibly bright distant objects called quasars. These things were tiny, yet they were blasting out more energy than entire galaxies. The only explanation that made sense was a monster, a supermassive black hole at their center, furiously gobbling up surrounding gas and dust. Suddenly, black holes weren't just theory anymore. They were the best answer to a very real cosmic mystery.
Around the same time, we found a suspect much closer to home.
In the constellation Cygnus, astronomers detected a powerful source of X-rays, named Cygnus X1. When they looked closer, they found it was part of a binary star system. One star was visible, but it was orbiting an invisible partner. By measuring the wobble of the visible star, they calculated the mass of its hidden companion. It was too heavy to be a normal star, and too massive to be a neutron star. The conclusion was inescapable. It had to be a stellar mass black hole, the collapsed remnant of a giant star. This was the first piece of solid, compelling evidence that these objects were truly out there, lurking in our own Milky Way galaxy. While astronomers were hunting for evidence, theoretical physicists were diving deep into the mind-bending nature of black holes. Giants like Stephen Hawking and Roger Penrose began to unravel their secrets. They weren't just simple cosmic vacuum cleaners. Hawking made a revolutionary discovery in the 1970s. He predicted that black holes aren't entirely black. Due to quantum effects near the event horizon, they should slowly leak radiation and eventually evaporate over immense timescales. This idea, known as Hawking radiation, transformed our understanding. It linked the massive world of gravity with the tiny, weird world of quantum mechanics, turning black holes from simple cosmic sinkholes into complex physical objects with their own temperature and entropy. As theories became more sophisticated, so did our tools for seeing the universe. We launched X-ray satellites like the Chandra X-ray Observatory, which gave us a new set of eyes. These telescopes could see the high-energy light pouring from the superheated material swirling into a black hole smaw, allowing us to map the violent environment right outside the event horizon. On the ground, radio astronomers developed a technique called interferometry. By linking telescopes thousands of miles apart, they could effectively create a virtual telescope as large as a continent, giving them the sharpest vision in astronomical history. This technology allowed them to track the orbits of stars and gas clouds at the center of our own galaxy, revealing they were all circling an unseen object with the mass of 4 million suns-hour, very own supermassive black hole Sagittarius A*. But even with all this progress, one holy grail remained. See a black hole's shadow. This required a telescope the size of the Earth itself, and that's exactly what scientists built. It's called the Event Horizon Telescope, or EHT. It isn't a single dish, but a global network of radio observatories, all synchronized with atomic clocks, all pointed at the same spot in the sky. From Hawaii to Spain, from the South Pole to Chile, they work together. So using a technique called very long baseline interferometry, they combine their data, effectively creating a planetary-scale camera capable of resolving an object as small as a donut on the surface of the moon. After years of painstaking observation and data processing, the moment of truth arrived. In April 2019, the EHT collaboration released an image that stunned the world. There it was, a glowing, blurry ring of superheated plasma encircling a dark, central void. This was the first ever direct picture of a black hole specifically, the supermassive one at the heart of the galaxy M87, 55 million light-years away. The image of that bright ring surrounding a dark shadow was a perfect match for what Einstein's theories had predicted a century earlier. It was a monumental achievement, turning an abstract concept into a visible reality and opening a brand new chapter in astronomy. Just as we were learning to see black holes, we also learned to hear them. Einstein had predicted that when massive objects like black holes collide, they should send out ripples in the very fabric of space-time gravitational waves. For a century, this remained another unproven theory, but in 2015, that changed. The Laser Interferometer Gravitational Wave Observatory, or LIGO, detected a faint chirp. It was the echo of two stellar mass black holes, spiraling into each other and merging in a cataclysmic event that happened over 1 billion years ago. This detection was a triumph. It not only confirmed another of Einstein's key predictions, but gave humanity a completely new sense to perceive the universe. We could now listen to the cosmic symphony of black hole collisions, studying them in a way that light could never reveal. This incredible journey, from a solution on paper to a picture from an Earth-sized telescope, has been a testament to human curiosity and collaboration. It took brilliant minds like Schwarzschild and Hawking, global teams of engineers and astronomers, and technologies that pushed the very limits of what's possible. We've gone from doubting black holes to imaging their shadows and hearing their cosmic collisions. Each step, whether it was a new equation, a new telescope, or a new detection, brought these mysterious objects out of the darkness and into the light of our understanding. And today, we're just getting started. We've entered the era of multi-messenger astronomy. This means we can now study a single cosmic event, like a black hole merger, using different kinds of signals simultaneously: light, X-rays, gravitational waves, and even tiny particles called neutrinos. It's like watching a cosmic orchestra with both our eyes and our ears, getting a richer, more complete picture than ever before. We're finally starting to tackle the biggest questions. How do supermassive black holes get so big? How do they shape the galaxies they live in? And what truly happens to the information that falls past the event horizon? The quest to understand black holes continues to drive science forward. They are the universe's ultimate laboratories, where the laws of physics are pushed to their absolute limits. Each new observation brings us closer to understanding not just these enigmatic objects, but the fundamental story of our cosmos. From mathematical oddities to cosmic cornerstones, the story of the black hole is a story of how we learn to see the unseeable. Hello, and welcome to a journey into the deepest, darkest future of our universe. What happens when all the stars have burned out? When galaxies have drifted so far apart they can no longer see each other? What remains when the cosmic lights go out for good? The answer is as profound as it is terrifying. The age of darkness, the era when only black holes remain. Our universe, as we know it, is not eternal. It's in a constant state of change. Stars are finite fuel tanks. Galaxies are slowly pulling away from one another, and the grand structures we see today are gradually dissolving. Over unimaginable timescales, the cosmos will fade. But as the universe descends into darkness, one type of object will emerge as the ultimate survivor: the black hole. Astronomers have a name for this distant, desolate epoch: the black hole era. It's predicted to begin tens of trillions of years from now. Long after the last star has sputtered out and the last galaxy has ceased to shine, imagine a universe almost entirely empty, a silent, cold expanse. In this profound darkness, black holes will be the last remaining titans, dominating a cosmos devoid of light. During this era, these gravitational behemoths will be the only active players. They will drift through the void, and when their paths cross, they will merge in titanic collisions, growing ever larger. They will act as cosmic vacuum cleaners, cannibalizing any smaller black holes, stray neutron stars, or forgotten brown dwarfs that wander too close. For eons, The universe will be a quiet dance of these dark giants.
Oh.
Their gravitational influence, the only force shaping what's left of reality. But even these titans are not immortal. The celebrated physicist Stephen Hawking discovered a mechanism that allows black holes to slowly die. It's a process called Hawking radiation, a faint glow of particles that leaks from the edge of a black hole, carrying away its mass, molecule by molecule, over incomprehensible stretches of time. This evaporation is an incredibly slow process. The smallest black holes, those born from the collapse of ancient stars, will be the first to disappear. They will slowly shrink, their faint radiation, a final whisper in the dark, until they vanish in a final, tiny burst of energy. The largest supermassive black holes, the ones that once sat at the heart of galaxies like our own Milky Way, will persist for trillions upon trillions of years. But eventually, even these cosmic monsters will succumb to evaporation, fading away until nothing remains. When the last black hole has vanished, the universe will enter its final state, a cold, dark, and almost perfectly empty expanse. It will be a silence beyond our comprehension, a cosmos governed only by the slow, aimless drift of stray particles in an endless void. Physicists call this the heat death, the universe's state of maximum entropy, where nothing interesting can ever happen again. Yet, there's a fascinating paradox in this story of cosmic decay. In this darkness, black holes act as the universe's ultimate archivists. They preserve a kind of memory of everything that ever was. Every particle they consumed, every star they devoured, every civilization that might have orbited those stars, all of that information isn't truly destroyed. It's believed to be encoded in some form, perhaps in the subtle patterns of the Hawking radiation they emit, or in hidden quantum states, or even in the very fabric of space-time they warp around them. They are in a strange twist, both the universe's destroyers and its final historians. This concept leads us to some of the most profound questions in physics and philosophy. Does information ever truly vanish from the universe? Or is it perfectly preserved in ways we just can't perceive? What is the ultimate fate of complexity, of structure, of meaning itself? And what does this all mean for consciousness, for life, and for intelligence? These fleeting, beautiful sparks that flicker for a moment in a cosmos destined for eternal darkness. From our tiny blue planet, nestled in a spiral arm of a vibrant galaxy, this future seems impossibly remote and abstract. We look up at a sky filled with stars, nebulae, and the promise of discovery. Yet, the story of black holes defines the complete life cycle of our universe, from the birth and death of stars to the shaping of galaxies. And finally, to the ultimate silence of all that remains. They are a powerful reminder that the cosmos is a place of both breathtaking creation and absolute destruction, of brilliant light and profound darkness. Even in the end, when gravity and silence are the only rulers, the story of the cosmos will endure, encoded in the last fading shadows of its final inhabitants. This is the age of black holes. It is the era when darkness rules. Gravity alone remains the final arbiter of existence. And in that ultimate silence, we glimpse a fundamental truth. Even in the total absence of light, even at the very end of all things, the universe still has a story to tell. Thank you so much for joining me on this journey to the end of time. If you found this cosmic exploration as fascinating as I do, please consider liking this video and subscribing to the channel for more deep dives into the mysteries of our universe. We'll see you in the next one.